RNN stands for Recurrent Neural Network. Unlike traditional neural networks that treat each input independently, RNNs are designed to handle sequences of data. The key difference? RNNs have loops. This loop lets them use information from earlier inputs, creating something powerful: memory. RNNs remember previous steps in a sequence. That memory allows them to understand context, such as the meaning of a word in a sentence or the trend in a time series. Let's start with a basic recurrent neuron. Imagine we have an input at time t, labeled xt, and the output yt. What makes this different is the hidden state, represented as ht. This hidden state carries information from the previous time step, which helps the neuron understand the current input in context. We call this unrolling the network over time, and it shows how the network processes and remembers sequences. Each hidden state, ht, is calculated using the current input xt and the previous hidden state ht1. The formula looks like this: ht ge activation by x xt plus y at 1 plus b, where x and wh are weight matrices, b is the bias, and the activation function adds nonlinearity. The output yt is then computed based on ht. RNNs can be structured in different ways depending on the task. We input a sequence, and the network returns a sequence. Perfect for tasks like time series prediction or language modeling. Here the input is a sequence, but we only care about one output, like a sentiment score for a movie review. The input is a single vector, such as an image, and the output is a sequence. This setup can generate image captions word by word. This powerful architecture encodes a sequence into a vector, then decodes it into another sequence. The encoder processes the original sentence, and the decoder generates its translation. While RNNs are powerful, they come with challenges. During training, gradients, which update the weights, can become too small or too large. Vanishing gradients: the network forgets early inputs. Exploding gradients: the network becomes unstable. To fix this, researchers created specialized architectures: LSTM, long short-term memory; GRU, gated recurrent units. These use gates to control information flow and keep gradients stable, allowing the network to remember important information over longer sequences. Another issue? Training RNNs can be computationally expensive. Since sequences must be processed step by step, training takes longer, especially for long inputs like paragraphs or audio. So to recap, RNNs are powerful because they remember. They're ideal for sequential data, text, audio, time series, and more. But challenges like vanishing gradients and slow training exist. Thankfully, LSTM and GRU architectures help solve these. Whether you're building chatbots, predictive models, or language translators, RNNs are the foundation of many AI breakthroughs. Thanks for watching. If this helped you understand RNNs, don't forget to like, subscribe, and hit the bell for more AI and deep learning explainers. See you in the next video.